Hello, everyone. Thank you for joining our LinkedIn Live. Today, we'll be discussing smart factory connectivity and PCBA test. Our host for this session will be John Arena, who's the product line director, Dennis Kang, our product marketing manager, and Charles Robinson, our senior applications engineer. And on that note, I'll pass it to John to get started.
Well, thank you, Christina, and thank you to our viewers here today on LinkedIn Live. This is a special COVID edition where all of our participants are squirreled away in their various quarantine locations. This is also relatively new for us, LinkedIn Live, but it's a way to reach out to our customer base and interested parties given the current environment in the world. So, Christina, I see a frozen screen. Thank you. So we're going to cover three topics here primarily. The first is our view of PCBA manufacturing and particularly the factory of the future in terms of what it means for the market that we play within, we participate in, and what it means for our customers. The second is to talk a little bit about the so what to factory of the future, and that is the concept of big data, the collection of more information about manufacturing, not just about the product, but about the environment in which the product's made, to try to improve productivity, get better communication on the factory floor in terms of machines that are not working up to par or maybe down or maybe waiting for product. Some of the most interesting breakthroughs that have occurred in this space is the availability of internal machine data as it relates to performance, which is another leading indicator of potential issues as they emerge. As systems get older, they need calibration, they wear. And lastly, we're going to set that up as a discussion about our own developments in the space of factory of the future, a product we call Smart4 Metrics, which is our data solution for factory of the future running on test station. There are three drivers today that are strong realities in electronics manufacturing. The first is electronics everywhere. This is nothing new. It's been the case for the last 30 years, but even the smallest appliances now come with an IP address and are able to be accessed over your smartphone. Part of that is the continued reduction in component size, the continued proliferation of computing power in smaller and smaller packages, the electrification and automation of motor vehicles and self-driving cars in particular. The automation of the home is already started. It's just in its salad days here. And the emergence of high-speed bandwidth applications such as 5G and improved versions of Wi-Fi. The next is the introduction of automation, both automation on the factory floor in the way of self-guided vehicles that can tote cargo, bring parts, bring finished goods, the introduction of multi-axis robots for the purposes of moving product or manipulating it for machining or manufacturing operations, and the introduction of automation as part of machinery. The third is the introduction of machine learning and artificial intelligence. Machine learning is a way in which computers can be taught to learn what good is and what bad is by training them. The most common cases are visual data, but it's applicable to even scalar data or matrix data as it applies in measurement. The idea being, if you show the machine enough examples of good and bad, it eventually acquires its own understanding of what those are and replaces the human eye and judgment. Having said all that, what's true today in manufacturing is that the front-end process, and by that I mean the portion of the PCB manufacturing line that is up to the reflow oven, including the inspection stage of the reflow oven, and back to the starting point, but not beyond. We call that portion the front end, and that's a pretty common industry definition. Those steps are sequential and linked. As each stage in that line adds value, there are quality steps at each point to evaluate whether the prior step was done properly. That product information is uploaded to the enterprise data system. That entire chain, that train of machinery is all linked together by SMEMA, and that includes coordinated equipment changeover, profile changeover, and tooling changeover to get the most productivity out of the front end process, which again is this long train of synchronized operations. That front end process develops two kinds of data. The first is, of course, product data. So in the case of solder paste, it's variables such as the solder volume, the solder height, the shape, etc. In the case of device placement, it's things like the rotation of the device, the coplanarity of the device, etc. And in the case of the reflow process, it's variables such as solder volume, solder wetting angle, etc. These are variables that are available today out of the machinery that performs the inspection. Those same machines now have internal to them environmental data, both the conditions inside the machine and the conditions just immediately to the outside of the machine. So in case of printing, it's variables such as the squeegee speed, the squeegee pressure. In the case of placement, it's the placement speed, the miss rate, the pick rate. And in the case of the soldering, it's the oven, the reflow oven profiles, the preheat, the post cool down, etc. Those variables are of great importance in Factory of the Future because they will help, first of all, identify errors when they occur, conditions that lead to a shutdown of the line, as well as the promise of higher productivity as we go forward. Let's take a look now at the back end of the line, which is that portion after the reflow oven. In that case, we have three common stages: an assembly test phase, an electrical test phase, a flashing phase, and typically an end-of-line function test. And again, product data is developed during each of those phases. In the case of the assembly test, it's variables such as, is there a short circuit? Is there a missing component? Is there a value that's wrong? In the case of flashing, it's checksum errors, load times, reflash rates. How many times has a part had to be reflashed more than once? And at the end of line, it's variables such as test time, test pass, test threshold, test limits. But again, these same machines produce tremendous amounts of internal data which heretofore has not been available to the enterprise to consider. In the case of test, it's things like internal temperature, vacuum pressures, compressed air pressure, operator name. In the case of flashing, again, it's temperatures, pressures, continuity errors, etc. And functional test has, again, internal temperatures, the operating rate, etc. These variables, like the front end, provide greater clarity into emerging problems. And when there is a hard fault that shuts the line down, you know immediately why that system might have shut down. Factory of the Future promises to harness not only the white data, the product data, but the orange data to provide a better view for manufacturing as to what's happening on the floor. Now, having said the similarities between the two, there's some very strong differences. The PCB front end is kind of like a train. All of the stages move in synchrony. Products travel left to right, and value-added steps occur. The work in process, which we'll call WIP for the purposes of today, is very low because the stages are all synchronous. The back-end processes in most applications instead are islands of individual function, an island of test, an island of flash, an island of end of line, and there may be other islands as they relate to assembly or manufacturing or added mechanical parts. These islands of manual work cells are a problem, as you'll see momentarily. The amount of work in process, buffer stock, that must be preserved to keep these islands running is substantial. And each one of these islands is staffed by typically a couple of operators that handle the product, keep track of the machine state, and try to keep the entire process running smoothly. But it's that same characteristic of islands of test that is the core problem. By having multiple systems per stage and multiple operators and multiple WIP buffers, you create the environment with a correlation between the time a new board or new product shows up at the back end versus the time it's actually processed is not synchronous, is not timely. And so the correlating the data and comparing the data as to when a problem occurred and when that board was manufactured is not as clear cut. Furthermore, remember that this stage is where, if defects are noted, there's a repair process, repair is executed, that board is returned back for retest, perhaps on an entirely different machine. So the environment there may change and the internal conditions may change. These differences do not lend themselves to a high productive environment. You've got operators, you've got work in process, and you've got this correlation problem I described earlier. If we look at the Holy Grail, what the factory of the future is drawn at in most experts' minds, it is a complete lights out synchronous line from solder paste deposition all the way to final assembly and test and end of line, with each system connected to the previous and to the next, communicating laterally where information can be of best use. So for example, if I'm putting down solder bricks in the front end, if I inspect them later and find them to be problematic and I can isolate it to a point in the stencil, tell the operator it's time for a stencil cleaning, or tell the operator that there's something wrong with the process, or adjust the squeegee pressure to compensate potentially. In the back end, if we see components fail, the same component fail on 2 or 3 consecutive boards, notify the operator there's something apparently wrong with the tester or the contact point where that component is located, because it's highly unlikely that that repetitive failure is by accident. So I've told you about the realities in manufacturing today, and I've told you about the view of the factory of the future, a lights out facility with relatively few operators needed. The reality is that today, this revolution is in its first generation. And while many companies have announced products, whether it's alliances, software solutions, or equipment solutions, there are no dominant universal working standards at present. And as Teradyne contemplates our offering, we're very keenly aware that this is very early going, and that most customers are not yet ready to make the initial investments necessary to institute Factory of the Future. It's very hard to make revolutionary changes in an industry that has proceeded to date by evolution. And this is likely going to take multiple years in our view. Lastly, even within the industry, many customers haven't determined themselves how in the world they're going to deal with the adoption of new technology. There's a measurement of this reality, which is called the hype cycle. The hype cycle is a way to... The hype cycle is a way to represent the reality versus the practicality of new technology. It's a term that was derived by Gartner Company to describe the emergence of new technology in terms of the promise and the introduction by the marketing teams and the reality as described by the engineering teams. The reality is that the marketing guys tend to oversell and overpromote, and the story is way ahead of the reality. That's true for Factory 4.0 as well. We believe, frankly, that we're near the peak of the hype cycle, and that reality is still years ahead in the future. To help explain why that understanding informs our view of how to develop a competent data solution, I'm going to turn it over to Dennis Kong, who will walk us through SmartForm metrics. Dennis?
Thank you, John. You probably, or maybe all the people connected to this call, maybe agree that Industry 4.0 is not simple word to define with a clear statement. Everybody has different ideas. In our test world, it's still evolving concept and extending trends in automation and data exchange with the industry's collective effort. We Teradyne, as a test solution provider, reliable testing and the measurement integrity are essential. As you know, the tester is the only the system, one of few manufacturing machines that execute the physical measurement by direct electrical contact on PCBA. It is truly a sensor technology in manufacturing that quantifying the quality with figures and numbers. So our first priority, we want to sustain our quality of the test measurement with the SmartPrometrics by providing comprehensive real-time monitoring feature to maintain the integrity of the testing and its data. Then our next mission will be make the test data highly accessible by neighbors, by customers, by suppliers, and by industry players. We believe that quantitative data in production will be crucial for reference point in the smart factory because smart factory needs intelligence, and the intelligence requires data. So the collecting and the processing the necessary data to create intelligence are important tasks. So more and more data connectivity, as you witness now, are needed. We design SmartPrometric to streamline the data connectivity development steps so much easier and so much less with so much less effort to make the data travel to any destination. So how is SmartPrometric is made? So we designed SmartPrometric as affordable and easy deployment solution. We want our inline solution, offline system, tester used by third-party partners to use SmartPrometrics because we are now acting as a sensor technology. Thanks to our engineering's great work, SmartPrometric can run if the tester is loaded with our latest Teradyne software platform on Windows 10. So no server is required, nor dedicated high-speed network bandwidth. Simply running SmartPrometric software installer on the PC, you can just install the software, then SmartPrometric is ready to run. So SmartPrometric consists of 3 core features. The first thing is universal open APIs. Universal APIs gives great flexibility to developers accessing our tester and the data. Data connectivity interface development has been always required substantial effort to understand process, hardware, and align protocols and message formatting, verification, and so on. But with the new comprehensive open APIs and the new database engine, development can be much faster and easier than before without expertise in our test system. The second thing is real-time monitoring. It provides comprehensive monitoring features, including hardware condition, calibration status, production statistics, KPIs, and can help users understand the situation for preventive and proactive maintenance to maximize machine utilization. As these monitoring features are running on the web application servers on the tester, you can access the tester and data by web browser within your network. As John mentioned earlier, there are so many emerging smart factory solutions and standards in our industry. Deploying a new solution and interfacing with the new solution with our existing equipment are quite challenging, as you already know. But that is very essential because everything has to be connected. So Teradyne provides pre-built standard plugins for easier and faster adoption to a popular smart factory standards such as IPC-CFX or popular commercial solutions. You can even have many solutions you already have. You have to connect to our system. We can work on that too. This can save customers and suppliers resource to make it work from scratch. We can save lots of save money and time. For example, currently IPC-CFX interface has been developed as a pilot project. It will be productized and available for customers. Hence, if customer introduce IPC-CFX in their manufacturing floor, Teradyne tester can be easily blended in by using plugin software. With the SmartPrometrics, we want to be a good neighbor with good source of data for customers, equipment, or solution suppliers as part of industry's collective effort. We want our reliable data available for data science, machine learning, and sophisticated analysis. So many other proposals coming up in the industry. So now Chuck has prepared some of the example of SmartForMetric real-time monitoring features. So Chuck, are you up? You're up.
Yeah. Thanks, Dennis. So as Dennis explained, there are a couple of different ways that a user may extract data from the tester, one in real time, giving you product data and machine data in real time, and also the web interface to give you an idea, a snapshot of what's been going on over time on the tester. So, but we also felt that we needed to provide our own data visualization on the system in order for you to get a quick snapshot of as what's going on with the tester. So this can be divided into a couple of different categories. One would be production monitoring. So this is a dashboard that will allow you to view your production efficiency, what your yield is, et cetera, different kinds of statistics. Also downtime statistics, which allow you to look at the utilization of the machine, is it being efficient or not. But you're also going to be able to look at the various hardware features of the system. So you'll be able to see, what's my calibration and OVP status? What are my input power levels, fan speeds, system temperature? And there's more sensors that we'll be adding over time, but this is just what we're working with in the current time frame. So you see to the right-hand side, a quick snapshot of some of those screens. I'm now going to go into a little bit more detail on two of the screens. So this is your real-time monitor. So this is your process monitoring dashboard on the tester. As Dennis mentioned, you can either view this on the tester or remotely via a web interface. So in the center of the screen, you see the most common KPI indicator, which is your OEE and its subcomponents, availability, quality, and performance. You also see across the top different information about identifying the machine, who the user is, what product's being tested, what's the temperature on the machine, how long it's been active, and is it active or not active, et cetera, right? To the right, you see production information. What's my target production rate? What is my current rate? What percentage am I sitting at? What's my test time? What's my cycle time? Again, information that's always important to know, and you can see it in real time. And then down on the bottom, you see the machine utilization timeline. So this shows uptime versus downtime, and then you're also able to see the various categories of downtime as to whether that's been scheduled or unscheduled, or maybe the machine's been planned to be out of production for a while. So again, these are components that go into your OEE calculation, but also in and of themselves, they're very important to measure as well, right? And an important point here is that this data is all stored in a database, so that at some later point in time, you can then access this database through the web interface and extract data for creating historical reports and things like that. And this is the main entry point in which you would jump to other additional dashboards available on the machine. So this is an example of our real-time maintenance dashboard. So as part of your system configuration, the user can set up various processes to be monitored, whether it be OVPs or calibration of various instruments in the system. They can also set the levels at which they want to be warned. I want to be warned 5 days before calibration is due. That's a simple reminder, but then if calibration is passed by so much time, then that's maybe an alert. And these alerts and warnings can be actually sent to the user via an email or a web alert or whatever. So again, the idea is you can be proactive in terms of addressing various maintenance and monitoring processes on the system. So in summary, or in a snapshot, what we're doing with SmartForMetrics is we are gathering important product, system, and process data and making that available to the factory ecosystem through flexible means, whether that be a standard like IPC CFX or some custom standard that's been developed in-house, or any emerging standards that might come up in the future. And also via that real-time web interface, you're able to extract data as well. So this is available now to the entire factory ecosystem, such that our customers have the ability to analyze what's going on the machine. They can cross-correlate data. This allows them to enhance productivity and then maintain a high level of productivity, and then feed that information back into their process to be able to improve and refine their process over time. And thanks very much for listening to our presentation today. Are there any questions?
Hi guys, thank you. So I'm just looking at the question pane here. Okay, so one of the questions is, if you're currently using your own dashboards and data analysis tools, can you still get your data out of SmartForMetrics, or do you have to use something within SmartForMetrics to access it?
No, as I just illustrated that we use a REST API for creating our web interface, and that will be published for customers to use to create their own web applications, to either create their own dashboards or for us to create future dashboards, but they can also extract data for analysis in whatever fashion they deem suitable.
All right, and then the next question I have is, if you're using something other than IPC CFX, including like maybe your own solution, can you still connect to SmartForMetrics, or is it IPC CFX only?
As Dennis mentioned, there is a general purpose API into the real-time data. So the real-time API is where you would get board validation, tester status, alerts about any faults that occur on the machine and things like that. So that would be a direct connection to the MES system, and again, that's an easy to develop API interface. Yeah. So that's the platform which we'd use to create custom applications or third-party applications.
Okay, and then I have another question here. It's, what sort of engagement are you getting from wave solder type process providers? The wave solder defect information is of high importance in some industries, so they're wondering what communication we're getting from that.
I don't think we've necessarily heard from wave solder vendors. Wave is obviously a technique that's been around a long time, and today it's done more as selective, or if you still have military or older through-hole type technologies, it's the predominant. From the oven side and profiles and temperatures and cool down, those would be the same as a reflow. They have the same or similar kinds of measurements. In terms of the inspection of wave solder, that's a harder proposition because the solder does not form as regularly as it does in a reflow setting. But if the data is available and we're able to provide a measurement that's relevant to it, would be happy to chat with any of the reflow solder vendors or the wave solder vendors or anyone in that space.
Okay, it looks like for now we don't have any more questions coming in, so I'll just see if any others pop up. In the meantime, if you do think of any additional questions, you can either, of course, reach out to us on LinkedIn, or you can send them directly to Dennis King, the product marketing manager, and his email is dennis.king@teradyne.com. Anything else you guys want to say?
I just want to thank our viewers for spending 30 minutes with us, now 33 minutes. This is a format that I think is going to be used for the foreseeable future to reach out, that travel and visits don't appear to be possible. So again, thank you for your time. We look forward to maybe another similar event coming soon to you.
All right, awesome. Thank you, as John said, for joining us, and we hope to see you next time.